First, I'd like to thank the organizers. I'm honored to give a talk here. Today, I will speak about algebraic automatic continuous fractions in characteristic 2. My talk is organized as follows. First, I will recall the notion of automaticity and their relation with algebraicity and transcendence. And then I will introduce continued fraction for power series and state our main results. Then I will give an example of the main result and the idea of the proof. Finally, I will talk about related results in the literature and the problems for further research. Okay, automatic sequences. As most of us are familiar with, a sequence is said to be D-automatic if it can be generated by a deterministic finite automaton with output. This is an 6 tuple that is composed of Q, a finite set of states, with Q0 being the initial state and sigma being the input alphabet, and we have the transition function delta and output alphabet big delta and an output function. This is an example of an automaton. It generates a sequence in the following way. First, we start with the initial state I. This is the automaton that generates the tumor sequence. To get the nth term of the sequence, because this is the 2 automaton, so we write n in base 2 and then we feed the digits of n in, or rather the bits of n in base 2 to the automaton, and finally what we get is the nth term of the sequence. Okay. So, automatic sequences, they are simple objects. From multiple points of views, they are simple objects. For example, one way to measure the complexity of a sequence is by its factor complexity, which maps n to the number of distinct factors of u of length n. So the theorem of Cobham says that the factor complexity of an automatic sequence is big O of n. This is just a little more complex than the most simple sequence that is ultimately periodic sequence. And then we have also this theorem of Cobham that says that if a sequence is both K and L automatic, where K and L are multiplicatively independent, then this sequence is ultimately periodic. So the interpretation of this theorem is that if an object is simple by 2 independent criteria, then it is trivial. So here, multiplicatively independent, it means that these 2 integers, they are not the powers of the same integer. For example, 2 and 6, they are multiplicatively independent. Mm-hmm. Okay. Now, here we can also see that automatic sequences, they are simple by another criteria. Here the theorem of Kristol says that a formal power series with coefficients in Fp, it is algebraic over Fp if and only if the sequence of its coefficients is p-automatic. So what does it mean for a power series to be algebraic? We can recall that when we say that a real number is algebraic, we mean that it is the root of a polynomial with integer with coefficients in Q. But here, when we say that something is algebraic over Fp of x, it means that it is the root of a polynomial with coefficients in Fp of x. So that is the okay. We know that the most simple numbers are rational numbers, and the numbers that are a little more complicated than rational numbers are algebraic numbers. So algebraicity is kind of a criteria for simplicity. And here we see indeed that the automatic sequences are also simple in this sense. And to prove this theorem, a key fact that we use is the following property of automatic sequence, which says that a sequence U is d-automatic if and only if its d-kernel is finite. So in the definition of algebraicity, there is a notion of finiteness. So where is the notion of finiteness in for algebraic series? It is the fact that if a series is algebraic if and only if the linear subspace generated by its powers has finite dimension. So in the proof of this theorem, in fact, we prove that the two notions of finiteness are the same. For example, let's see. Let's take f with where the coefficients is the two-mode sequence. Let's see why f satisfy an algebraic equation. So we write down f. In the first step, we divide f into two parts. So we have the even terms and the odd terms. Then we use the relations of the kernel of the sequence. The even term is the sequence itself. The odd terms, we have this relation. And then after simplifying, what we get is indeed a polynomial relation between f and f squared. This is a polynomial equation where the coefficients are rational fractions. So we have f squared, and 1 of them. Okay. And then we have also the following two theorems, which says that the real case is completely the opposite than the finite characteristic case. Here, the theorem of Adamczewski and Bureau says that an automatic real number, that is to say, a real number whose base B expansion form an automatic sequence, it is either rational or transcendental. Okay, and then the same is true for the continued fraction expansion of an algebraic number, of a real number. If we have a real number alpha, and if the partial quotients of alpha form an automatic sequence that is not ultimately periodic, then alpha must be transcendental. This results, one would expect such results to be true. And why is that? Because if we recall what we said below the theorem Cobham, if an object is simple by two independent criteria, then it is trivial. Just now we said that algebraicity is also a way of being simple. So if something is automatic, p-automatic, then it is simple by this criteria in the finite finite field. So it means that if it is not trivial, then it cannot also be simple for the real case. So. And then those are the theorems that I learned when I was a student. But then I felt that something was missing, because now we get to the second part of my talk. Because just as real numbers, formal power series can also be written as continued fraction. Here we have a series that is, notice that it is in 1 over z, so that the positive part is finite and the negative part can be infinite. We define the integer part of the series to be the polynomial part. And then we can use the continued fraction algorithm to find its partial quotients. Here the partial quotients are polynomials. In real case, partial quotients are integers. Yeah. So this process is exactly the same as finding the continued fraction expansion for real numbers. So I wondered what is the relation between the automaticity of partial quotients and the algebraicity of the series. And those are what we found. First, with Han, we began by the most classical case of automatic sequence, the Tumor sequence, and the period doubling sequence. We recall that here the Tumor sequence is the fixed point of this substitution, and the period doubling sequence is the fixed point of this one. We found that the continued fraction that they define are indeed algebraic, but we were only to prove this for some cases. What does it mean that for some cases? It's because normally the Tumor sequence, the terms are 0 and 1s, but what we want for the partial quotients should be polynomials. So we need to choose a polynomial for 0 and choose another polynomial for 1 for this sequence to define a power series. For example, we could take 0 to be z, we could take 1 to be z plus 1. And then we form the Tumor sequence here, and then we will have a power series. So we can see that there are infinite choices for polynomials, for mapping 0 and 1 to polynomials. And with Han, we were only able to prove a finite number of cases. And then Bujold and Han were able to prove that the two most continued fractions are algebraic for all choices of polynomials. And then Lajonias and I proved that the period doubling continued fractions are also algebraic for all choices of polynomials. And then I gave a generalization to these results. So so now we have two classical automatic sequences that define algebraic continued fractions. What about, is it true for all automatic sequences? So we started by looking at other classical examples of automatic sequence, but they do not seem to be algebraic. So how can I?
Over F2.
Yeah. Yes. Yes, of course. You can. Yeah. I didn't see it. Thanks. Just everything here. Yes, when we are talking about algebraicity here, the K in our case is F2. Yeah. Okay, and so now is how can I find more automatic sequence that define algebraic continuous fractions? So we found one way to generalize the pure doubling sequence. So instead of defining it by the substitution, we choose to look at the pure doubling sequence this way. We see that it is the limit of this sequence of finite words. We can see that it is generated in this way. They are in the middle in blue. It is 0, 1, 0, 1. And it will continue this way. It is periodic. It is 0, 1. Okay. And then at each step, the new word is composed of the old word and the blue thing and with the old word repeated. So to put it more precisely, let W0 be the empty word, let epsilon be 0, 1 to the infinity, and define the next word to be Wn, epsilon n, Wn. Here the comma is for concatenation. And then the pure doubling sequence is the limit of Wn. So to generalize the pure doubling sequence, we consider other sequences that can be defined this way. That is, we start with W0 being any finite word and epsilon any periodic sequence. Then we define Wn plus 1 by this relation, and what we obtain is a sequence that is an analog to pure doubling sequence, and we let this be the sequence defined by the initial condition Wn 0 and epsilon, and we let P denote the family of such sequences. This is one way to generalize. And then the next thing that we notice is that the trimal sequence, it is the sum of the pure doubling sequence. More precisely, the nth term of T is the sum of the first n terms of P modulo 2. So that is to say, if I define sigma to be the operator that maps a binary sequence to this sequence, and then T is sigma of P. Okay, so now P is good, T is good. So if I apply sigma multiple times to P, do we also obtain a good sequence? Yes, the answer is yes, and we can do more general than that. In fact, we does not only consider the sum of P, we also consider all the sum of elements in P. We consider all the sums, all the iterative sums of from the sequences that are generalizations of the pure doubling sequence. And in this way, we obtain a larger family that we call G, which can be defined this way. First, let epsilon be a periodic 0-1 sequence, and we start with U0 and V0 to be two non-empty finite words. And for the next terms, we define Un plus 1 and Vn plus 1 depending on the value of epsilon n. If epsilon n is 0, then we repeat them. If epsilon n is 1, then we alternate them. So from this definition, we can see that the trimal sequence belongs to this family. The trimal sequence is defined by U0 and V0 equal to, U0 is 0, V0 is 1, and epsilon for the tumor sequence should be, it is 1, it is all 1 for the tumor sequence. Okay, so now we found the two families of sequences that are good. But before stating the main results, I will first introduce a little more notation, because since we said that, just now we said that to consider the continued fraction in data power series that is defined by the sequences, first we need to map the term of the sequence to polynomials. So there is a question of the choice of polynomials. But then I realized that why bother mapping the terms to polynomials? We could just regard the terms of formal variables. So then later we adopted this notation instead. So here A is the finite alphabet where my sequence takes value in, and then all the letters are treated as formal variables. So we use this. We have this notation for the multivariate polynomial ring, the multivariate fraction field, and then the ring of formal power series. There is something that we should be careful about, is that when we have only one variable, this thing is a field. But when we have more than two variables, it is no longer a field, it is only a ring. Okay. So now, how do we define a continued fraction? Here UN, the sequence UN is a sequence that takes value in my alphabet A. So in this case, the continued fraction is defined as the limit of the convergence. It is defined by the continued fraction. We can see that it is the definition of continued fraction. For example, if we truncate to the term U2, what we obtain is, by definition, it is this thing. If we expand it, we get an element in the here. Okay. So that's for the notation. And now we are able to announce our main results. Is that when we have a sequence for sequences in P and for all sequences in G, all these sequences define algebraic continued fractions over F2 of A. And moreover, the degree of algebraicity is bounded by 2 to the n, where n is the period of epsilon, and here the k is the period of epsilon. So, okay, recall that the P, when we apply sigma to P, we found a sequence in G, but when we apply sigma to sequences in G, we are still in G. So we do not get more sequences by applying sigma to sequences in G. And what about the inverse operation? What if instead of taking the sum, I consider the difference? If I take the difference of a sequence in G, then we believe what we find is transcendental, but we cannot prove it. Okay, now we get to the third part of the talk. I will give an example of the proof. I will give an example of a particular case of our result, and then I will give the general idea of the proof. First, for the notation and the proof, we define a matrix N to be the multiplication of these n+1 matrices. And then by the definition of continued fraction, the nth convergent is simply the quotient of two components of the matrix. Here, this Mn01 is the 0,1th component of the matrix Mn. In general, the numerators and denominators, they do not converge, but the quotient as a whole, they converge. They always converge, as in the real case. Okay. So now let's look at the two-more sequence. Let's prove that it defines an algebraic continued fraction in F2 of X. This example for that the algebraicity holds for all polynomials was first proved by Bujold and Han. And now here we give a simpler proof of this, and that use the that is the same as the way we proved our general result here. So just now we said that if we make these initial conditions and we take epsilon is 1 to the infinity, then the sequence that we get is the two-more sequence. If we define M0 corresponds to the U0 and the W0 corresponds to the V0, and we define inductively Mk as follows, and then by the definition of continued fraction by this relation, we have that the two-most continued fraction is the limit of this thing. To prove that this continued fraction is algebraic, here, in fact, not only the quotient converges, but the numerator and the denominator, they also converge in themselves. So we will just calculate the limit of M2k plus 1. The key of the proof is such a relation is a relation between M3 and M1. For the moment, let's not look at the blue part. I will come back to the blue part later. So we have this relation where D, R, and CL are some constants. And then the next thing that I realized is that the relation star holds, it does not depend on M0 and W0. It's not, the relation does not depend on the particular form of M0 and W0. So in particular, I could take M0 and W0 to be M2 and W2. In this way, I could get a relation between M5 and M3. Okay. Now my new M0 and the W0 are true. So now I get a relation between M5 and M3. And when I continue this way, I can get the general expression for M2k plus 1. And we can see that there is a pattern that we can see clearly. So finally, if I define F to be this thing and H to be this thing, then the limit of M2k plus 1 is just this thing. But this is obviously algebraic because F it is here. We can see that F4 is nothing but F divided by L. And from the definition of H, we can also see that H4 over L2 is nothing but H minus D. Just by the definition. Okay. And then we have finished the proof of algebraicity for the two-most continued fraction. Just now we said that the key of the proof is a relation of this form. Now we choose to write it in this way for the general, in order that it looks similar to the general case. For the general case, we need to find such relation for every possible epsilon. Here epsilon is always periodic. So here the m, my m, it is a sequence. It is a sequence indexed by integers. But when we change the epsilon, it is not enough to have a sequence of m, but instead, for the general case, what we need is a matrices m indexed by finite binary strings that corresponds to the period of epsilon. We still define it by induction, so that if we have a zero, if we add a zero, we take the square. If we add a 1, we alternate. And then the key relation in the general case looks like this. So this, where the Cj are the coefficients that depends on S. So for every given epsilon, I can take the S to be the period of epsilon, and we obtain a relation in this form, and that will be our key relation from which we will deduce algebraicity. Okay, that is all for the proof, the idea of the proof. And next, I will talk about the related results in the literature. So our point of view is we started with automatic sequences, and we looked at the continuous fraction that they define. But there were early works that starts from algebraic series. And this goes back to Bauman's suite. And since then, it has been studied by various other authors, such as Mills and Robbins, Alouche, Kawar, Lajonias, and Yao. So within the literature, there are examples of algebraic power series whose partial quotients are automatic, but they are not always automatic. Sometimes they are morphic, but not automatic. Sometimes they are regular, but not automatic. A sequence is regular. It is regular sequences are generalizations of automatic sequence. A sequence is automatic when its D-kernel is finite. A sequence is deregular when its D-kernel is a vector space of finite dimension. Okay. But our work is something that did not exist in the literature, because in the literature, even when an algebraic sequence has automatic partial quotients, so in this case, the partial quotients of polynomials, when we change the polynomials, we believe that they are no longer transcendental, even though we did not prove it. But experimentally, it is very not likely that they are algebraic. So what we found were the only sequences that are known to be algebraic for all choices of polynomials. Okay, and finally, this list also, we can see that there is still a lot that we do not know about the link of automaticity and algebraicity and or algebraic continuous fractions in general. So then we have all these problems for research. For example, I would like to classify the algebraic continuous fractions by their partial quotients. We just mentioned that sometimes it is automatic, sometimes it is regular morphic, or sometimes I don't see a pattern at all. And okay, and then I also mentioned multiple times that we believe that such sequence define an transcendental continuous fraction, but we were never able to prove it. So how to prove transcendence? And also I would be interested in classifying automatic sequences. There are those that we find that define algebraic continuous fractions for all choices of polynomials, they are the ones that define algebraic continued fraction for some choice of polynomials, and maybe there are ones that never define algebraic continued fractions. And also, for the this question is related to this one, for the algebraic series whose partial quotients are not only automatic, but they are automatic and belong to the first class of automatic sequence. What's special about this algebraic power series? And also, finally, another question is, how does the partial quotient sequence of algebraically conjugate series relate? For example, if I have an algebraic series, and I know that its partial quotients are automatic, if I consider its algebraic conjugate, will the partial quotient also be automatic or not? So I remember that from what I've seen in my experience, it's not always the case. We do not always have automaticity for our conjugates. Okay. That is all. Thank you.
So please, there's time for questions.
Thank you for the talk. There was this theorem 4, and it was kind of bugging me because my poor brain couldn't think of an example for automatic real number that's rational. Could you give me an example to?
Because periodic sequences are rational. Yeah, periodic sequences are automatic.
Yeah, of course. Okay. Sorry. Thank you.
So, some other questions?
Thanks for the talk. Is all of this particular to characteristic 2, or does any of it generalize to higher characteristic?
For our results, it's only in characteristic 2. But for the examples that in the literature, there are also results in there are also automatic partial quotients for algebraic series in odd characteristics.
And any odd characteristic?
I think so. Yeah.
Thanks.
Follow-up question. Characteristic 2 means that it need not be F2, it can be
Yes.
to anything.
Yes.
Okay.
Thank you. There are some variations on automatic sequences when you use not just usual positional systems, but okay, so you don't see me, but something more general, and maybe the most well-known example is Fibonacci automatic. Okay, so okay, you can substitute any other. Are there any results of this sort if you consider this type of automaticity?
Fibonacci is like the Fibonacci word, or?
I mean, in Fibonacci system, you have this unique form of representation of a number with no subsequent ones, and you have the same type of automaticity. And
I have never considered this question before, but I think it is possible because here we see that the partial quotients, they are sometimes automatic, sometimes morphic, sometimes regular. So maybe there is a more general class of sequence that contains all this, which include all algebraic series. It is possible.
Okay, thank you.
Thank you.
Okay, so any other question? If there are no more questions, then thank you again.
Thank you.